So anyways, today we're going to finish up section 1.6. You'll be able to do the homework for 1.3.1.5. That's due on Friday. Homework 1.6, I thought was due Friday, but it's due next Friday. So you'll have a little bit extra time on that, but you'll be able to do it all today, after today. So 1.6 and then 1.3.1.5. Those two homeworks, I would suggest trying to get done this week. Definitely the 1.3.1.5 because that is due, and we've already covered all of that. But probably 1.6 after today, and we'll also get most of the way through a couple of these other sections. All right, so we're dealing with absolute value functions. And we're going to get to absolute value functions, but first, we were solving the absolute value equations, right? And we said if we had an absolute value equal to a number, if that number were negative, there'd be no solution to the equation, just like we saw in example 2, one of the ones in example 2. But if we solved and got absolute value equal to some non-negative number, then we create two equations, where the inside component could have been the number itself, or the inside component could have been the negative of that number. And then obviously we solve each case. So that's what we did last time. We saw that in a few examples. Now we can also expand that out to inequalities. When we expand it out to inequalities, it's going to work in a very similar way. We're going to isolate the absolute value on one side or the other. For these types, there's obviously more complex types of absolute value questions, but for the types we're going to look at, we're going to have variable inside the absolute value. And that's the only place the variable is going to be. So we're going to isolate the absolute value on one side of the equation. And then we look at the inequality. If there's nothing that works, we say there's no solution. If there are things that work, then we break it into two different pieces. Okay. Now, the thing you have to remember about inequalities is if you have an inequality like 5 is less than 7, whenever you multiply both sides by a negative, it flips the sign. Negative 5 is bigger than negative 7. Okay. So whenever we multiply or divide both sides of an inequality by a negative number, then we flip the sign. And that comes to play when we create our two inequalities as well. And I'll demonstrate that with these examples. So let's take a look at these two examples. We have x minus 2 inside of absolute values set greater than or equal to 10. And then x plus 1 inside of absolute values minus 14 is less than 2. So for this first one, we already have the absolute value isolated. This side has to be non-negative. Therefore, so the left-hand side has to be non-negative. So we can get positive numbers here. Those positive numbers can be bigger than 10, so it's going to make sense. Now, this means I need to break it into two different inequalities. If both of these inside pieces are, if the inside piece is positive, let's put it that way. Let me phrase this. If the inside piece were positive, then I haven't really done anything. So I just keep the symbol the way it is. If this inside piece is negative, when I set x minus 2 and compare it to negative 10, that's basically like a multiplication on both sides by a negative. Does that make sense? And so I have to flip the sign when I do that. Well, that's weird sounding, but this is going to be the case every single time. When we're dealing with the positive of that number, we keep the sign the same. When we take the negative of that number, we'll flip the sign. Okay, because it's like multiplying both sides by a negative. And now I just do my standard thing of solving, add 2 to both sides. That doesn't change the sign. We get x greater than or equal to 12. Over here, when I add 2 to both sides, I get x less than or equal to negative 8. Now, these are sort of two independent inequalities. What I mean by that is that if you look on the number line, we have negative 8 and positive 12 here on the number line. To be less than or equal to negative 8 would mean we're to the left of negative 8. To be greater than or equal to 12 means we're at 12 or above. So 12 or above, 12 to the right, negative 8 to the left. And this is what it looks like on a number line. Now, before we go any further, forgot this. I wanted to show you what it looks like on Moodle, all right? Because I don't, I don't want to throw you off. Basically, what I do on Moodle, this one had variable y instead of variable x, but same deal. We say larger numerical answer is y, and then you pick out your inequality symbol. So for us it was x greater than or equal to 12. So we'd have picked greater than or equal to 12. And then the smaller answer would have been x less than or equal to -8. So we'd have picked less than or equal to -8. Okay, and that would have been the answer. And then you'd pick out which it looks like. Okay. These two numbers split our number line into 3 sections, and essentially what happens is we either get the middle third or we get the outer 2 sections. We get the middle 1 section or we get the outer 2 sections. And that's what this is asking you for. Like, visually speaking, do you get the middle section or do you get the outer 2 sections? Okay. So that's what it looks like when we solve inequalities and what Moodle is going to ask for. Or how Moodle is going to ask for the answer. That's pretty straightforward, I think, but that's what I wanted to put up. You could, if you wanted to, use interval notation as well. These aren't the only notations. You can use set notation. If you did want to use interval notation, that would be -infinity up to -8. And then from 12 to +infinity. That would be the interval notation if you wanted to use that. I don't ask for that on homework, but wow, that's another notation we could use. And we see. All right, the second question asked us to solve this inequality, adding 14 to both sides. Gives x plus 1 inside of an absolute value is less than 16. The number on the right is positive, so I'll split it up in the usual way, which is say x plus 1 less than 16 if we keep the positive, or x plus 1 greater than -16. Again, when I use the negative number, I flip the sign. When I use the positive, I keep the sign the same. Right? That's the big thing. That's the big takeaway. In this case, add 1, or excuse me, not add 1, subtract 1 from both sides. Subtracting 1 doesn't change the sign. We get x less than 15. Again, and or x greater than -17. In this case, basically on a number line, -17 is obviously to the left of +15. You can't touch 15. You don't want we don't have the equal to signs, so we draw open circles. Again, this is not the biggest deal. But notice that we're saying x has to be smaller than 15. X has to be greater than -17. This is where I get the middle section. Right? So I get the middle section in this case. Whereas I got the two end sections on that case. Again, if you wanted interval notation, you'd do -17 up to 15, and then you'd have to put parentheses on both sides. These are kind of the two different options as far as answers go in these absolute value inequalities for the most part. When I get a positive number, when I get absolute value, and on the right-hand side, a positive number, these are the two options. Any questions about that? All right, let's take a look at these two. Now, these two are almost identical except for the signs that we use. We have 5 times the absolute value of x plus 3 greater than or equal to -10. And then we just change the sign to less than -10 in the second option. So 5 times the absolute value of x plus 3 greater than or equal to -10 in the first one, and then 5 times the absolute value of x plus 3 less than -10 in the second. So for both of these, I would start out by getting rid of this coefficient in front of the absolute value. I would divide both sides by 5. I'll do that over here as well. Dividing by a positive doesn't change the sign, so we're going to end up with an absolute value of x plus 3 is greater than or equal to -2. And then in the other one, we have the absolute value of x plus 3 is less than -2. So in these two, we have absolute value on one side, negative number on the other. Right? That's the key point. On the one on the left, what works? What can you plug in for x? Add 3 to it, take an absolute value, and it be bigger than or equal to -2. -5 would work. How about 32? Sure. How about -1400? Sure. Because when you take -1400 plus 3, then take the absolute value, you get a big positive number. In other words, what I'm trying to get at is whatever happens on the left-hand side, it's going to end up non-negative. It's going to end up positive or 0. Okay, I'm just going to write positive for, it's not exactly that, but so we have something that's positive no matter what we plug in for x, greater than or equal to negative. So what I'm explaining is that this is always going to be true no matter what x value you plug in. So the solution for this one is all real numbers. anything you plug in for x is going to give you a positive on the left-hand side. And that's always going to be greater than or equal to a negative. That's always true. Okay. On the other hand, in this second problem, we get a positive, technically a positive or a 0. Less than -2. That's always false. Right? 5 is not less than 2. 38 is not less than 2. -2, excuse me. 5 is not less than -2. 38 is not less than -2. So this is always false. And you know what that means too. That means no solutions. And again, symbolically, you might see something like the empty set in the book, or if you're reading in a book somewhere. So when we have a negative on the right-hand side, we end up essentially getting either the all real numbers or the no solution option. Okay? Depending on how our inequality sign is pointing. If our inequality sign is pointing and saying, well, this positive thing is always greater than or equal to -2, that's always true. If we have something that's going to be positive always saying it's less than a negative, that's always false. So there we go. So if you have a negative on the right-hand side of an inequality, you end up with, right? So it doesn't always have to be on the right. You can flip-flop. But if you have absolute value inequality negative, you end up with either the all real numbers or the no solutions. That's the point. That's the point that I'm making. So those are kind of the two that are weird. When you get absolute value isolated, and then on the other side, we have a negative. Usually, we'll get absolute value isolated, and on the other side, we'll end up with a positive number. Okay? And that's like the first examples we did today, where we had either that middle section or the outer two sections being our solutions. I want you to try these two inequalities on your own. Solve these, see what you end up with. See if you can refresh that. And if you do need assistance, let me know. As soon as I write these on the board, I'll walk around with it. All right, let me go through each of these. So first off, on this first one, to isolate the absolute value piece, we would subtract 5 from both sides. You would end up with absolute value of x plus 3 is less than 1. And then, since we have a positive number on the one side, on the right side in this case, we can say that x plus 3 is less than 1 and or x plus 3 greater than negative 1. So we use 1 and negative 1, and then we flip the sign when we use the negative 1. That's like multiplying both sides by a negative. Solving each of these, gives me x is less than negative 2 and or x greater than negative 4. What I do is I draw this on the number line. Negative 4 is to the left of negative 2. And then I look for whether my inequality includes the equal sign. If it includes the equal sign, then I fill in the circle. If it doesn't include the equal sign, I leave the circle open. And then I know I'm going to have to either fill in the middle or the two outside edges. In this case, we want less than negative 2, greater than negative 4, so that's the middle part. Anything in between negative 4 and negative 2 is going to work. On the outsides of that, it's not going to work. On this second one, I would start by subtracting 4 from both sides. That gives a negative 2 times the absolute value of x minus 1 is less than or equal to negative 12. And then we have to divide both sides by that coefficient of negative 2. Now, here's the trick. If you divide by a negative on both sides, you have to flip the sign. So, since we divide by negative 2 on both sides, we have to flip the sign. That was different from our last couple of examples. Oops, didn't flip the sign. We haven't had to do that yet until that last stage. Yeah.
Why wouldn't we divide by negative 2 first instead of subtracting 4?
Oh, you could have done that as well. If you did divide by negative 2 first, you have to divide this, this, and this, all 3 terms. So you could have done that as well. Just traditionally, when we solve an equation, traditionally when I do it, I get all of the terms on one side and then I divide by the coefficient. And so, but you could divide by the coefficient and then move terms around. But you should get the same thing even if you divide off everything by negative 2 and then move things around. Should get this at the end. At this point, since we have absolute value, inequality symbol, positive number, we can set x minus 1 to be greater than or equal to 6, or x minus 1 less than or equal to negative 6. Again, sign flips when I have a negative sign in there. When I use negative 6, I flip the sign because that's like multiplying both sides by negative. Adding 1 to both sides gives me 2 inequalities. The first of which is x greater than or equal to 7. The second is x less than or equal to negative 5. Again, negative 5 is to the left of positive 7. Because we have the equal symbols, I'm going to fill in the circles. And then this says x greater than or equal to 7, so I'm shading to the right. Less than or equal to negative 5, so I'm shading to the left. Everybody understand why I'm pointing arrows the way I'm pointing them? Okay. By the way, if you're ever in doubt of where to point the arrows, all you have to do is pick a number in the middle or pick a number on the outside and plug it into your original inequality and see if it gives you a true statement. So for instance, the number 0 is in there somewhere in the middle, right? So I could have plugged 0 in for x and see what happened. Let me go ahead and do that. Negative 2 times absolute value of 0 minus 1 plus 4 less than or equal to negative 8. And if we did that, the left-hand side, this becomes a 1 after you take the absolute value. So negative 2 times 1 is negative 2, plus 4 is 2. This says 2 less than or equal to negative 8, which is false. So I know we shouldn't shade in the middle. I get that. So you can always test by just plugging in a middle number, or you could have plugged in an outside number. If I'd have plugged in 8 or 9 or 10 or whatever I wanted to, let's say I plug in 10. Then we get, that's a 9, absolute value of 9 is still a 9. Negative 2 times 9 is negative 18, plus 4 is negative 14. So I get negative 14 less than or equal to negative 8. That's a true statement. So I knew I should have shaded where the 10 was. So if you're ever in doubt, you can just pick points in whatever section, pick numbers in whatever section we're at, plug them in and see if you get a true statement. Here you could have plugged in a negative 3 and you ended up with 5 less than 6, that's true. So shade in the middle. Or if you'd have picked a 0, you would have ended up with something that's false. So you don't shade where 0 is. Okay with that? So if you're ever in doubt, just pick a number, test it, see if you get a true statement or a false statement. You should shade where the true statements are, not shade where the false statements are. Now, inequalities is not the main point of this section. Remember, the main point of this section is to examine and deal with absolute value functions, these transformations of our base absolute value function. So we did transformations of the base absolute value function last class period. Now, what we can do, since we know how to solve absolute value equations, we can now take that knowledge and use it to calculate the x and y intercepts for an absolute value function. We already know that on any function, some key points are the x and y intercepts. Right? X-intercepts are where our graph hits the x-axis. So those points are all going to have the form x comma 0, since it moves 0 in the y direction. Functions could have no x-intercepts sometimes. It could have one x-intercept. It could have lots of x-intercepts. Absolute value functions will have 0, 1, or 2. Y-intercepts are where our graph hits the y-axis, graph of our function hits the y-axis. In general, you can have 0 or 1 y-intercept. Remember why we can't have 2 y-intercepts?
It wouldn't be a function.
Wouldn't be a function, failed the vertical line test. So we either have 1 or 0. In these absolute value functions, we're going to have 1 always. Right? Because there's no gaps in the absolute value functions that we're going to look at. Okay? Now, I don't think I've mentioned this yet. Maybe I have. I can't remember. When we talk about x-intercepts, x-intercepts are those points which have form x comma 0. Right? If I have a function, that means if you input the x value, you get out 0. We call those x values zeros of our function. So the x-intercept technically is the point x comma 0. Those x values are zeros of the function because when you plug them into your function, you get out a 0. Again, that's just a linguistic thing. You can deal with that in whatever way you like. But if the homework asks for an x-intercept, and then the homework asks for a 0, remember those values of x are interchangeable. They're just a little bit distinct in what they're asking for. X-intercepts the point, the 0 is the x value. Okay. All right. And I think we know this already, but I'll mention it again. Since all of the y-intercepts have the form 0 comma y, in order to find a y-intercept, we just plug in 0 for the x value. And if we want to find the x-intercept, we plug in 0 for the y value. Finding the x-intercepts is equivalent to finding the zeros of the function. So because we have these points, x and y intercepts, those are key points to any function. Where we cross the x-axis, where we cross the y-axis. To find y-intercepts, plug in 0 for x. To find x-intercepts, plug in 0 for y. And solve. What this means for our absolute value function is that we're going to be solving absolute value equations after we plug in the 0. All right, to find the x and y intercepts. Now, knowing the x and y intercepts are nice because, well, in the last section, we graphed using transformations. You can also graph using points. And again, some of the key points of interest are usually the x and y intercepts. There's other points of interest too on an absolute value function, like the vertex. That's where the change in direction, the point of the v is. But x and y intercepts are important as well. So let's take this function, f of x equals absolute value of x minus 3 minus 5. And we'll find the x and y intercepts, and then we'll graph the function. I'm going to find the y-intercept first. On this absolute value function, because it's a nice continuous function, you're always going to get one y-intercept. Whenever we find the y-intercept, we're going to plug in x equals 0 into the function. So plug in 0 into the function. 0 minus 3 minus 5 becomes, that's going to be a positive 3 minus 5, which is a negative 2. So plugging in 0 gives me out a negative 2. That means the y-intercept is the point 0, negative 2. Let's take a look at the x-intercepts. For this function, we plug in 0 for y. That's just the output of x, right? So that's my y. So I can plug in 0 for y. I get a 0 is equal to the absolute value of x minus 3 minus 5. And then this is just solving an absolute value equation. 5 to both sides. I get 5 is equal to the absolute value of x minus 3. Or if you prefer, you can write the absolute value on the left-hand side and say absolute value of x minus 3 is equal to 5. Doesn't matter. In either case, this is a positive number. So we do our same thing. We let the thing inside the absolute value equal the positive number, or we let the thing inside the absolute value equal to the negative of that number.
Can that be x minus?
Oh, did I say? Yeah, I miswrote that. Should be a minus there. Yep. Adding 3 to both sides gives us 2 answers, one of which is x equals 8. The other is x equals negative 2. Now, those 2 numbers are the zeros of that function. If it asks for x-intercepts, you're just writing 8, 0, and negative 2, 0. If it asks for the zeros of the function, it's just the numbers themselves. So there we go. Y-intercepts, x-intercepts. We're good to go. If you wanted to graph these by hand, this function by hand, what I would probably do is I'd probably in my mind think, okay, we started with an absolute value function. How was it transformed? That minus 3 would move it right 3 units. Minus 5 would move it down 5. So my vertex is right here somewhere, right 3 down 5. And then if I didn't want to by hand draw the thing, I can say now I know I have x-intercepts at negative 2, 0. So there's 1. And at 8, 0. There's another. And then 0, negative 2 is my y-intercept. So I have this point, this point, this point, and that point. And I know the transition happens here, right? I know the transition happens here. So if I drew this by hand, I get that. Normally, I don't ask you to draw things by hand on the homework because we do have access to the TI-84 calculator. We do have access to Desmos on homework too. There you go. Any questions about that? All right. Now, here's what I'm going to do. Don't worry too much about graphing the function, but I would like you to try to find the x and y intercepts of this function using the same algebraic techniques we just did. So here we have a function h of x is equal to 2 times x minus 8 plus 10. All right, so let's go through this. If I'm finding the y-intercept, I'm plugging in 0 for x. So this x gets replaced with a 0. I end up with 2 times the absolute value of 0 minus 8, and then plus 10. When you calculate that, you end up getting 16 plus 10, which is 26. Is that right? So the y-intercept is 0, comma, 26. To find the x-intercept, we plug in a 0 for y. Now, you could write 0 equals this, or this equals 0. 2 times the absolute value of x minus 8, then plus 10 equal to 0, or 0 equal to that. Oftentimes, I like having my absolute value on the left-hand side of the equation, just because that's, again, a little bit more traditional, so that's why I wrote it that way. In any case, when you solve, you would subtract 10 from both sides, and that would leave you 2 times absolute value of x minus 8 is equal to negative 10. And then we divide both sides by +2, which gives absolute value of x minus 8 is equal to a -5. Now, when we were solving absolute value equations last time, we solved things like this. What type of solution is this? No solution, right? The thing on the left is never going to be negative. It's always going to be positive or 0. So we have no solution for this equation. And that means there are no x-intercepts. And that means there's no real numbers that I can plug in to my function and get out a 0. Linguistically, we say there's no real zeros. Nothing, no real numbers I can plug into my equation to get out 0. So no real zeros. That's what we say. And when you think about what this does, what this equation does, in terms of transformations, it takes our standard absolute value function and it moves it to the right 8 units and then up 10 units. Right? And then there's a 2, which is a vertical stretch. So I should have said right 8, vertical stretch, up 10. And so I know I don't have my tick marks right, but it'd be doing something like this. It'd be pointing up. At the lowest point here, this vertex point, would be 10. I think I got that right. And we're pointing up, so it's pretty obvious that it's not going to cross the x-axis. All right. Again, I'm not being real precise with that because that wasn't the point of the question. So this is the scenario in which we can get no x-intercepts. That's the whole point, right? And we get no x-intercepts precisely because of the shape and where that function sits. There you go. Ooh, sorry. So it sits right up there. So it's never going to come down and cross the x-axis, right? That's the idea. Let's do another. Let's find the zeros and the y-intercept of the following function. This is called g of x. You don't have to graph it. I'll graph it on Desmos at the end, just to confirm that we got the right thing. Or maybe I'll graph it on TA84 to confirm that we got the right thing. Go ahead and try this one as well. Find zeros and the y-intercept. Remember, zeros is just the term for the x values of the x-intercepts. At least when we have real numbers. Slightly different when we don't. Alright, people seem to be doing pretty well on these, so let me do this. I'll go through it pretty quickly. When we're trying to find the y-intercept, we plug in 0 for x. Two times 0 is 0, minus 1 is -1. Absolute value of -1 is positive 1, times 3 is 3, minus 6 is -3, right? So we get g of 0 as a -3. You can also type that in on your calculator if you're you want to do that. Just have to use the absolute values. That's fine. That's a function or a calculator. So that means the y-intercept is 0, -3. I'll show you that when I drop down the screen and graph. The x-intercepts are the zeros of the function I get by plugging in 0 for the y value. And again, normally I'd put 0 equals 3, but since I like having my absolute value on the left-hand side, I'll put 3 times the absolute value, 2x minus 1, all minus 6. I'll put that equal to 0, where 0 is on the right-hand side. Add 6 to both sides. Then divide by 3. The 3's over here on this one first term cancel, and now we have the absolute value of 2x minus 1 isolated, and then that's set equal to 2. Now I can do my standard solving of absolute values by saying that that means the inside piece could have been equal to 2, or the inside piece could have been equal to negative 2. By the way, in our inequalities, we flip the sign. But we don't have to do that on the equalities, right? Because flipping an equal sign is still an equal sign. So, make any difference. All right, so we'll add 1 and then divide by 2 in each case. Divide by the coefficient of 2. And depending on how Moodle wants it, well, I know how Moodle's going to ask for it. Moodle's going to ask as a decimal rounded to 2 decimal places. Okay, it's going to ask for the decimal rounded to 2 decimal places. So the zeros here are when x is equal to 3/2 or 1.5, written as a decimal, and x is equal to -1/2 or -0.5 as a decimal. Again, I don't care how you write it on your notes. That's not a big deal. But on Moodle, just whatever way it asks for it, give it that way. And I know in this section, in particular, it's going to ask for decimal rounded to 2 places. So there you go. Those are the zeros. This question asks for the zeros rather than the x-intercepts. But if you wanted to write the x-intercepts, you could also have written the x-intercepts. The x-intercept is 1.5 comma 0 and -0.5 comma 0. So there they are graphed. By the way, this one's a little bit tricky because a lot of times when people look at this g of x, they think the vertex is going to be, oh, move it over 1 and down 6 because they'll ignore those stretching, the horizontal and vertical stretching. Because of this horizontal stretch of 2, it actually is only moving the vertex over 1/2 of a unit and down 6. Because of the way that stretches and moves. Some people will do this, they'll factor out that 2 and they'll view it like this. And that's a horizontal stretch of 2, but you notice moved right 1/2 of the unit. So The vertex is going to be a half a unit over. And we can check that on your calculator too. Anytime you want to graph or anytime you want to calculate, you can do that on your calculator. So just to illustrate what I did when I plugged in x equals 0, you can go 3, and then in the math menu, scroll over to number, absolute value. Mine has math print operating system. So it's going to look like the absolute value bars. If you don't have that, then it just says ABS. Not a big deal. And then 2 times 0 minus 1 minus 6. That's a -3. So you can do that on your calculator if you don't want to do it in your head, like I did on the board. You can do it on the calculator. Okay. You can also graph absolute value functions by just hitting y equals 3. Go back in, get the absolute value, 2x minus 1 minus 6. And then there you go. Oh, I don't have the, let me zoom standard first. That'll probably look a little bit more like yours. And then you can see what's happening. Notice, again, like I said, that vertex, that very bottom point, is a half, comma, -6. But there you go. You can see 0, -3 there. You can see -0.50. You can see 1.50. All that kind of good stuff. All right, any questions about that? Finding zeros, finding x-intercepts, finding y-intercepts. Nothing? Okay, good. That's very nice. All right, so I'm going to stop section 1.6 right there. And now we're going to go back to section 1.4. So section 1.4 is about function operations, and the key operation that we're going to focus on, I should say the key, but one of the key focus operations is the function composition, right? So it's the operation of function composition. Because that function composition operation, that'll lead us to function inverses, which is our next thing. There we go. So the first operations we're going to look at, the first operations are our standard mathematical operations of adding, subtracting, multiplying, and dividing. If we have 2 or more functions, we can add them up. We can multiply them. We can subtract them. We can divide them. And whenever we do that, all we're doing is we're adding or multiplying or subtracting or dividing the outputs. So the expression for the outputs or the numerical outputs of the individual functions. So we're going to add, subtract, multiply, divide the outputs. That's what it means to add a function. It means to add the outputs. Add, multiply the outputs, subtract the outputs, so on and so forth. So we take the expressions that give us our outputs and we do that to them. Okay. Now, notationally, what we'll see is that when you add functions f and g, we are going to create a new function called f plus g. And this new function called f plus g of x is just the output of f of x plus the output of g of x. When you subtract, it works the exact same way. We create a new function called f minus g, and we get the output by taking the output of f minus the output of g. When we multiply, we use some multiplication symbol, but it's just f times g. Sometimes we write those just right next to each other. Sometimes we put the little dot in between them. Sometimes we put the times symbol in between them. But just like you would expect, you take the output of f and you multiply it times the output of g. So we get output. Usually when we divide functions, we write something like f divided by g as a fraction in that first case here. You can use the division symbol, that's less likely, but it's just the output of f divided by the output of g. Now, the one thing we have to worry about when we divide is we have to worry about dividing by 0. So this is defined so long as our denominator is not 0. So long as the output of g is not 0, then we can do that. And if g of x was 0, then we just restrict the domain so that we can't plug in 0. But that's the notation, again, fairly intuitive notation that we're going to use. So let's take an example. We have f of x is equal to 3x minus 4. And g of x is equal to x squared minus 1. We'll add, subtract, multiply, divide. When we subtract, we'll do f minus g. When we divide, we'll do f divided by g. When we add, f plus g. When we multiply, f times g. And this is all with an arbitrary variable x as our input. So f plus g of x, f minus g of x, and so on and so forth. All right. Oh, that's the wrong button. There we go. So the concept here is pretty straightforward. we just take the output of f of x and add the output of g of x. Since the output of f of x is 3x minus 4, and the output of g of x is x squared, minus 1, we simply add those two together. And then that's it. F plus g of x. So this is a new function called f plus g. And it has the output of, well, I'll combine like terms and write them in order. X squared plus 3x minus 4 minus 1 gives me minus 5. There you go. So very intuitive to add two functions together. To subtract functions, the one thing you have to watch out for. So I won't write this second step very often moving forward, but I will write it right now. When you subtract functions, you're subtracting g of x, not just the first term of g. So when you subtract that function, make sure you subtract x squared minus 1 entirely, and you don't just subtract x squared. Follow that. So in other words, put parentheses around the x squared minus 1, and that negative is going to distribute to both terms. So that's the only thing to watch out for, really. Other than that, fairly straightforward. F minus g of x. I have a negative x squared. This is a plus 3x. This is a minus 4, and then that's a plus 1. So that becomes a minus 3 when I combine like terms. F times g of x. I'm just going to multiply the two outputs. 3x minus 4 times x squared minus 1. If I do this, I'm going to have to remember how to multiply polynomials, essentially. Every term in the left-hand polynomial multiplies times every term in the right-hand polynomial. So I'll go ahead and do that. X squared times 3x is 3x to the third. Then I'll do an x squared times negative 4. Then I'll do negative 1 times 3x. And then negative 1 times negative 4. And that's the output. Does that make sense? So that's the output there. And there's no like terms. If there were like terms, I'd combine it in another step. But in this case, there's no like terms to combine. What if we have f divided by g of x? Well, all we're going to do is write 3x minus 4 and divide it by x squared minus 1. You can simplify that or rewrite that if you want. This one doesn't simplify well, but you could rewrite it in a number of different ways. For the purpose of this class, don't worry about doing long division or anything like that. Just write it, leave it like that. Now, one thing I want to point out to you, let's say that was our answer, 3x minus 4 over x squared minus 1. To some problem in Moodle that we have to type. That's fine. Okay. Well, that's. I'll have a division one. Shoot, written here. That's fine. I'll do it here. All right. So let's pretend there was a division problem that I had. This is obviously multiplication, different functions. But let's say I had to write 3x minus 4 divided by x squared minus 1. Okay. If I typed in 3x minus 4 and then divide slash x squared minus 1, what's going to happen is it's going to obey order of operations. And it's going to do the division first. And it's not going to write the entirety of 3x minus 4 over the entirety of x squared minus 1 if I type it in like that. So all I have to do is use parentheses to make sure my numerator has 2 terms and to make sure my denominator has 2 terms. So just put parentheses around the numerator, parentheses around the denominator if we are typing something like that. And as far as this class goes, at this stage, we know that there are certain numbers I can't plug into that. I can't plug in a 1 because the denominator would be a 0. I also can't plug in a negative 1 because the denominator would be 0. But I don't need to write that. I don't need to write that at this stage. Does that make sense? So this function that I have written on the board, which is f divided by g of x, does have a restricted domain, but again, that's not the important thing to this section. Now, what if I have f plus g of a number? Something like f plus g of 3. F minus g of 3. F times g of 3. F over g of 3. There's actually a couple of different ways to approach problems like this. If I wanted to find f plus g of 3, one way is to say we just figured out the expression for f plus g of x. So I could, if I want, figure out f plus g of 3 by plugging it into this thing. I think I got 13 there. All right. Try and do that in my head. So I got a 13 now, right? So I already had this expression plug in 3. I could do the same thing here. F minus G of 3. And plug it into this expression, negative 3 squared plus 3 times 3 minus 3. And that gives me out a negative 3. Okay. I'll go through all of them. F times G of 3. I already know this expression, so I could just plug in 3 into that expression. Get whatever number that is. I'll do that on my calculator. I got a 40. Okay. And then I could have done the same thing here. I could have figured out this expression and then calculated oh no, what did I do there? There. Sorry. What is 3 squared minus 1? Or it's all 8. So 5/8. By the way, that's 0.625 is decimal. Doesn't matter which way you write that at this stage. That's not the point. Okay.
I typed in the multiplication one and got negative 239.
Which one?
The multiplication one.
I think you should get 40 now. You get minus, and then plus.
It was written as multiplication up there. The second minus, so that's what we wanted.
Oh, yeah, yeah. Yeah, that should be a minus and a minus there. Minus 4 times 3 squared minus 3 times 3. Pretty sure it should. And here's how you can actually do it the other way. Here's how it's actually might be easier, especially in the multiplication case. Let's say I didn't already have this expression multiplied out. If I didn't have this expression multiplied out, or if I didn't have this expression already written down, if I didn't have this expression already written down, this f plus g of x. Let's say I didn't know that. Well, what I could have done, if I didn't know that expression, is I could have simply plugged in 3 into each function separately. And in this case, added the outputs. If you plug in 3 to f, you get a 5. If you plug in 3 to g, you get an 8. 5 plus 8 is 13. What about subtraction? Well, when we subtract f of 3 minus g of 3, that is 5 minus 8, which is negative 3. That's especially useful if I didn't already do all that work. What about here when I multiply? Well, when I multiply, oops, we're going to get f of 3 times g of 3, which is 5 times 8, which is obviously 40. And then when I divide, we know what's going to happen. This way. We got f of 3 divided by g of 3, which is 5 over 8, or 0.625. I won't write it as a decimal. I'll just leave it as 5 over 8 right now. So in other words, if I know that when I plug in 3 into f, I get a 5, and plug in 3 into g, I get an 8, then figuring out f plus g of 3 is just adding 5 and 8. F minus g of 3 is 5 minus 8. F times g of 3 is 5 times 8. F divided by g of 3 is 5 over 8. That makes sense? And that is a lot faster if you only had to do that. Now, if you had to also find f plus g of x, and you had to also find f minus g of x, then it might be faster the other way. But it's always a good check if you did it the other way to just think through it this way too. So for instance, that multiplication problem that we did, if I got out something that wasn't 5 times 8, I know that'd be a red flag, right? That'd be something that's definitely off in some way, shape, or form. So here's what I'm going to ask you to do. I'm going to ask you to find the specifics for f plus g of -1, f minus g of -1, f times g of -1, f divided by g of -1 for these two functions. And then do the general version and see which one's easier. Makes sense? Same two functions on both pages. So that's example 2 and 2b. Let me get the specific ones. I always think in a situation like this, to me, it's easier to do the specific because these functions have lots of terms. And so when you just start doing the general version of it, it gets messier with lots and lots of terms, especially when things like you're multiplying, you get lots and lots of terms. But when you're adding and subtracting, it's not a huge deal. But when you're multiplying, you get lots and lots of terms. If you did want to like simplify and rewrite it with division, then you can end up with some messy stuff too. But with the specifics of inputting -1, you can simply plug in -1 into this. This would be -1 cubed minus 2. That's going to be a positive 1. So -1 minus 2. This is going to give me a positive 4. And then plus 7. And when you do that, you get 8. When I plug in -1 here, this will give me a positive 1. This will give me a minus 5. This will give me a plus 9. Turns out you get 5. I know it's taking 2 numbers. That's just happenstance. But now, if somebody asks you what's f plus g of -1, all you have to do is say, well, that's f of -1 plus g of -1, which is 8 plus 5, which is 13. And it goes real quick with specifics. Same thing if we subtract f minus g of -1 is going to be 8 minus 5, which is which is positive 3. Excuse me, last one was -3. This is positive 3. By the way, be careful on the order of that. This is f minus g, not g minus f. And I did G minus F there for a second. F times G of -1. F of -1 times G of -1 is 8 times 5, which is 40. F divided by G of -1. I'm just going to go to the last step. Well, no, right. I'll write the steps, might as well. A over 5 would be, yeah, 1.6 if you wanted a decimal version. So 8 over 5, that's the improper fraction version. 1.6 is the decimal version. So I think the specific ones go really quick. Sometimes the more general thing, and that's what I'll do now, goes a little bit slower. When we add f plus g, we're going to add this polynomial to this other polynomial. And then combining like terms, you get x to the third minus x squared plus 1x plus 16. By the way, you know what? One way to check that you got the right thing is to plug in -1 and see if that equals 13. That makes sense. So plug in -1, -1, -1, another -1, so -3 plus 16 is 13. Yeah. At least it matches up with -1. When you subtract those two polynomials, you just have to remember to distribute that negative sign into every single term. We're going to get x to the third. I'll do this in my head. -x squared minus x squared is a -3x squared. Minus 4x minus 5x is minus 9x. And then 7 minus 9 becomes a -2. Again, if you wanted to plug in -1, see that you get out a 3. If you do, you're probably on the right track. F times g of x would be these two polynomials multiplied times each other. When you do that, you get a lot of terms. That's fine. A lot of terms is just a lot of terms. You could go through this x cubed, I'll multiply the x cubed by everything, and then the -2x squared by everything on the right, then the -4x by everything on the right, and 7 by everything on the right. I'll try to do that as quickly as I can. I know it's really boring to do all that. busy work, but we'll go ahead and try it. We got x to the 5th plus 5x to the 4th plus 9x to the 3rd, that's 1. And if I'm okay with using multiple lines for meaning the same thing, what I can do is I can take negative 2x squared times x squared is minus 2x to the 4th minus 10x to the 3rd minus 18x squared. This is the same line, I'm just writing it underneath so it's easier to add up. And then minus 4x times everything is going to be minus 4x to the 3rd minus 20x squared minus 36x. And then 7 times everything, 7x squared plus 35x plus 63. And then if I write it like that, it's a little bit easier to add up like terms because I've already aligned them. I'm just writing one line with all the like terms lined up using multiple lines, obviously. All right, so we got x to the 5th plus 3x to the 4th minus 5x to the 3rd minus 31x squared minus 1x plus 63. And if I'm in doubt, try to plug in a -1. See what you get. Or maybe another number, you know. See what you get. We know -1, so we should get 40 when we plug in -1. And -1 plus 3. This will be a plus 5 when we plug in the -1, this term. This would be a minus 31 when I plug in -1. This would be a plus 1. And this would be a plus 63. When I added all those up, I got 40. So that's not a guarantee that I did it right, but it's pretty good evidence that I did it right. And then if I'm dividing, I'm not going to simplify if I'm dividing. I'm just going to write x to the 3rd minus 2x squared minus 4x plus 7, and I'll divide that whole thing by x squared plus 5x plus 9. You can rewrite, simplify if you want, but I'm not going to. Yeah,
I typed the addition one into decimals, so I got 15.
typed in when you plugged in -1, you're saying?
Yeah.
Okay. I ended up getting -1. This should be another -1, and this should be another -1, and then plus 16. Something so you should have a -3 plus 16, which is 13. Check your type in. And I'll type it in.
Isn't the x supposed to be a negative?
What's that?
No, I read it wrong. Never mind, I messed up. Does not mean.
Okay, yeah, just a type in, yeah. I think it should. Yeah, that's why sometimes it's really nice to plug in some numbers and have that as a good check, because it's very easy to throw off a sign and get thrown off. Like you put a plus 31 instead of a minus 31x squared, and then everything's wrong. And in Moodle, it's kind of an all or nothing thing, as you've probably seen already. Right? It gives you either this is not the correct answer or this is the correct answer, and there's no, hey, you've gotten 6 out of, you gotten 5 out of the 6 terms right. 6 out of the 7 terms right, or whatever. So it's kind of unforgiving in that way. All right, so in these 2 examples, the first 2 examples we've done, we had the explicit formula for F and the explicit formula for G. So we had the function's output written as an expression in X. But even if you don't have the function's output, let's say that there's some function F out there. And all I know is that when I plug in a 5, I get a -3. And there's some function G out there, and all I know is that when I plug in a 5, I get a 12. I can still do F plus G, or F minus G, or F times G, or F divided by G of 5. If I wanted to do F plus G of 5, all I have to do is add -3 to 12, which gives me a 9. If I do F minus G of 5, all I have to do is take -3 and then subtract 12. That's a -15. If I were doing F multiplied times G of 5, all I'd have to do is multiply -3 times 12. And that would give me a -36. And then F divided by G of 5 would be a -3 divided by a +12, which is -1/4 or -0.25 as a decimal. By the way, in each example that I've done, my example 1, my example 2, my example 3, I always did F minus G. If you did G minus F, you just subtract in the opposite direction, right? That shouldn't be a big thing. Same thing when we divide it. If I did G divided by F, that's legitimate to do. You just take 12 over -3. So when you multiply, the order of multiplication doesn't matter, but when you subtract, when you divide, order matters. So be careful about that if on the homework it does G minus F, or if it does G divided by F. So. And then obviously the operations can get more complicated as well. We could have something like g divided by f of 2 in this scenario, knowing that f sends 2 to 6 and g sends 2 to 11. Let me go ahead and write this down. F sends 2 to 6, G sends 2 to 11, and we want to find G divided by F of 2. That's pretty obvious. What we need to do, we need to take 11 and divide it by 6. We haven't gone over multiplication by a constant number yet. At least not explicitly. But I bet you it's the exact intuition you think. All right, so if I get g over f of 2, that's 11 over 6, and that's like 1.83 repeating, something like that, decimal wise. Let me look it up. 11 over 6, yeah, 1.83 repeating. If I do this, it's exactly what you think it is. It should be 4 times f of 2 minus 8 times g of 2, which in this case, 4 times 6 minus 8 times 11. By the way, is this operation any different than what we've done so far? It's not really. It's actually just the same operation we did with function multiplication, but we think of 4 as being the constant function of 4, right? So it's just output's always 4, just multiply everything by 4. So that's 24 minus 88, or negative 64. And again, that's the same concept over here. We're taking f times g minus 3 times f. This is just the constant function 3. So that's like taking f of 2 times g of 2 minus the constant 3 multiplied times f of 2. 6 times 11 minus 3 times 6. So that's 66 minus 18, 48. And you can imagine that we could do this with expressions as well. You can multiply by constants, you can combine different operations like function multiplication, function subtraction, multiplying by a constant. Lots and lots of different operations you can combine when you're doing this function arithmetic. All right? Obviously, I did it with a numerical value of 2 is the input, but you can do it with the arbitrary x as the input as well. Now, the thing that we're going to do next time is function composition. So we'll do function composition next time, and then we'll see how that relates to inverse functions. Okay. Don't forget about homework. There's one homework due this Friday, but if you want to complete the 1, 3, 1, 5, and the 1, 6, you can do that this Friday. 1, 6 is technically not due until next week, but you guys all can do 1, 6 right now. Any questions about anything? All right, make sure you get that homework done. Other than that, I'll see you next week.